Hello, students. Let's start with a question. Have you ever thought about what happens to matter when we keep breaking it into smaller pieces? If you could slice a grain of salt a billion times, what would you finally get? Early chemists and philosophers believed the answer was the atom, a solid, indivisible particle making up all matter. But as new technologies emerged, especially in the 19th century, scientists discovered that the atom was not the final building block. Experiments using electricity and mysterious rays began to show that atoms themselves must be made of even smaller, hidden components. This realization launched a whole new era of discovery. Imagine the idea that something as ordinary as air or water is made of particles too small to see, yet complex on the inside. The hunt for these subatomic secrets changed science forever. One of the greatest breakthroughs came from J. Thomson, who wondered why a glass tube, called a cathode ray tube, would glow when high voltage was applied. Have you ever seen old television screens? They glow for the same reason. Thomson's experiments showed that the rays inside the tube traveled from the negative end, the cathode, to the positive end, the anode. When he placed electric or magnetic fields nearby, these rays bent, revealing they were made of tiny, negatively charged particles. He called these particles electrons and calculated their charge to mass ratio. To put it simply, electrons are thousands of times lighter than atoms themselves. So, the atom wasn't solid, it was filled with even tinier particles. This discovery completely changed how we understood matter. Let's picture an atom as a desert. After finding electrons, Thomson proposed the plum pudding model. Imagine a spherical pudding where the dough is positively charged and the plums are negatively charged electrons scattered within it. In this model, the positive and negative charges balance out, making the atom neutral. This was a clever explanation for why atoms don't carry any overall charge even though they contain negative electrons. But as scientists continued their experiments, new results showed that this model was incomplete. Not everything could be explained by spreading out positive charge like a soup. Curious minds wanted to test Thomson's model further. Enter Ernest Rutherford, who designed a brilliant experiment in which alpha particles, tiny, positively charged bullets, were fired at an extremely thin gold foil. Most alpha particles passed straight through the foil, but a few bounced back or were deflected at large angles. This shocked everyone. If the plum pudding model was right, nothing should have bounced back. Rutherford realized that nearly all the mass and positive charge of the atom had to be concentrated in an ultra-small, dense center, the nucleus. The rest of the atom was mostly empty space with electrons whizzing around. What makes the nucleus positive? That's because it contains protons, fundamental particles with a positive charge. A proton has the same amount of charge as an electron, but it's positive and is about 1837 times heavier. The number of protons in a nucleus gives each atom its identity. For example, hydrogen has one proton, helium has two, and so on. Protons determine an element's atomic number and its place in the periodic table. So, when you look at fireworks bursting in different colors, you're seeing energy released by electrons moving in atoms with different numbers of protons. Still, something was missing. If only protons and electrons existed, atomic masses didn't add up. In 1932, James Chadwick solved this mystery. He found that the nucleus also contains neutrons, particles with no electric charge, but almost exactly the same mass as protons. Neutrons act as the glue, holding the protons together inside the nucleus. Without neutrons, the repelling positive charges of protons would make the nucleus fly apart. Neutrons also explain why many elements have atoms with different masses but identical chemical properties. These are called isotopes. For instance, carbon 12 and carbon 13 both have 6 protons but different numbers of neutrons. Let's take a step back and see how these discoveries changed science. Dalton imagined the atom as a solid sphere, Thomson thought of it as a pudding filled with electrons, Rutherford revealed a tiny dense nucleus, and Chadwick completed the picture with neutrons. Today, we know that an atom consists of a nucleus made up of protons and neutrons, with electrons arranged in shells or energy levels outside. The total atomic mass number equals the number of protons plus the number of neutrons. So, for sodium 23, that's 11 protons and 12 neutrons. This structure explains why some elements are reactive, some are inert, and why atoms are neutral overall. Let's quickly review what we've discovered about the structure of the atom. Uncovering electrons, protons, and neutrons unlocked the secrets of the elements, from electricity lighting your home to radioactive isotopes saving lives in hospitals. Knowing the number and arrangement of these subatomic particles helps scientists design new materials, understand why metals corrode, and even date fossils using radioactive carbon. Remember, chemistry is more than equations. It's the key to understanding the invisible machinery inside every object, every living cell, and every device around you. I hope you now see how atoms, with their hidden worlds of particles, shape everything you experience. Catch you in the next class where we'll reveal more fascinating stories of matter and molecules.